So that is connected across the phase. And CC is the current coil that would be connected in series with the phase, right? So this is one phase of the load, another phase, another phase. So to find the power, we need to find the current through that phase and the voltage across that phase. So this is the 1 watt meter method, right? And what will be done now is that you find it in this phase, and then you go ahead and find it in the next phase, and then you find it in the third phase, and then you add up all of them, right? And this will be the formula that governs that calculation for the reading that the wattmeter would be showing. So it's the voltage across the phase times the current through the phase and that power factor difference. All right. If it's a balanced three-phase system, then the total power is equal to 3 times the power in one phase. All right, and that will be something that you know from before. All right. I showed you before this star system. This slide is showing you also for the delta system how the wattmeter would be connected for a delta system. I want you to pay some attention to what is called the polarity marks on the wattmeter. They're actually...
Sir.
Yes.
Good afternoon, sir. A student wanted to let them in, sir.
Oh, all right. I didn't see a message. Let me... I don't see anything. The student is still around?
I think the student is in now, sir.
Oh, may have been in then because I didn't do anything a while ago. All right. So the polarity marks indicated in this case by a plus V shows you the end of the coil that is positive with respect to the other end, right? And that positive or polarity mark, which can be a dot also. So when we later on when we doing transformers and that kind of thing, you will also see that. The polarity mark could be a dot or it could be this plus here. So this is telling you that when current enters at this terminal through this at this point, this end is positive with respect to the other end. All right, so that's what the polarity mark is telling you, and that's a very important thing to note because it will determine how we consider the phasors, right? So that's what this last line is saying. The direction of the phasor is indicated by the polarity marks, right? So notice it's also here on this one. So as I said before, it can be dots or it could be a plus sign to tell you which end is positive when current enters into that end. Again, so the total power, if this is a balanced system, you just need to find one phase and multiply by 3. All right, and there are some formulas here for power, as which you would know already, for real power, reactive power, and apparent power. All right, so just giving you some pictorial. So this one would now be the use of 3 watt meters to measure the power in the 3-phase circuit. So each watt meter will be measuring what's happening in each phase, right? So it's kind of intuitive that yes, the 3 watt meters can be used to determine the total power in the 3-phase system. So you just find what's happening in each phase and add them up. So these are all single phase watt meters and they're connected in each phase, right? So this is the top one is for the top circuit is for a star system, and the circuit below is for a delta system. So 3 watt meter method. All right. So you can understand that this would make intuitive sense. 3 watt meters can measure power in each of the 3 phases. Similarly with the 1 watt meter, you just find it in one and use 1 watt meter and go around and measure it for each phase. But 2 watt meters can also be used to measure the total power in a 3-phase system. And this circuit now shows you how both watt meters are connected. Notice that the watt meters are measuring line voltage. So the voltage here is between A and C, and A would be at the higher potential. Right. So this voltage would be VAC, right? And for the second watt meter, the voltage is again a line voltage between B and C. So this voltage here would be VBC also. Now notice that the watt meter voltage coils are connected. Both of them are connected to line C, while their current coils are in line A and line B respectively. This has to do with the theory of the 2 watt meter method, right? So notice how the connections are done. You have one line where both common ends of the voltage coils are connected to, and then the other 2 lines would have the current coils connected in them. All right. And you could choose any 2 lines to have the current coil connecting, or any line to become the common. Any line could be chosen. All right, so I had pointed out that watt meter 1 was reading VAC, but if you remember the sequence that we have been operating with, we have been using red, yellow, blue, but it's the same as ABC. The Americans use the ABC sequence, and the British use the red, yellow, blue. But basically it's just names. They are basically telling you the same thing. All right, so our sequence would be for these line voltages would be VAB, VBC, and VCA rotating anticlockwise. But notice now that this voltage is VAC, right? So the first letter is the higher potential, and it indicates where the current would be flowing from the higher potential down, right? But our sequence says that it should be VCA. So, but we are measuring VAC. as you know about phasors or vectors, if you change around the subscripts, you're basically changing the direction by 180 degrees. So VAC is actually minus VCA. All right. And we will use some of that when we get into calculations in a little while. All right. The three-phase load could be star or delta. So if it's a star system, though, it's a three-wire system for the use of the 2-watt meter method. All right. And this follows from a theory, Blondel's theorem, which basically states that if you have n conductors, so in this case we have 3 conductors, then we need n minus 1 single phase watt meters to measure the total power in the system. So 3 lines, 3 conductors, we need 3 minus 1, 2 watt meters to measure the total power in a 3-phase system. All right. And how we connected, I told you already. So he specified how the watt meters should be connected. The voltage coil for each watt meter must be connected to a common point. And then the current coils would be in the other 2 lines, right, as shown. All right. All right, now from the theory of the 2-watt meter method, the total power can be given by the readings of each, the sum of the readings of each watt meter. So I call PW1 as the power measured by watt meter 1 and PW2 power measured by watt meter 2. All right. For a 4-wire system, according to the theory, we need 3 watt meters. But I must say that if for a star system, which would be where you have the 4-wire system, if the system is balanced, if it's a balanced star system, then you can use the 2-watt meter method, because no current will be flowing in the neutral conductor in that case. All right. And the theory says that for a 3-wire system, the 2-watt meter method can be used to measure both balanced and unbalanced load. All right. And this is some reference to Blondel's theory and how you measure power. You can click on that when you have a chance. Oh, by the way, the notes is in the Google Classrooms. All right. So let's get into a question. This question says that 3 non-reactive loads are connected in delta across a 3-phase 3-wire 400 volt supply in the following way. So 10 kilowatts across the red yellow lines, 6 across the yellow blue lines, and 4 kilowatts across the BR lines. We should calculate the power measured by each watt meter and then the total power drawn by the 3-phase load. All right. I put this point here in bold, but I won't necessarily always put that, because I will assume that you know that we're operating in this sequence: red, yellow, blue, anti-clockwise. All right. So I will go through this solution and then I will give you a chance to do some practice for your own. All right, so it's a delta connected system and the supply voltage is 400 volts. 400 volts, right? So VRY, we're gonna, since this sequence is red, yellow, blue, anti-clockwise. VRY then will become our reference phasor. VYB would be at angle 240 and VBR at angle 120. All right. And just as we found out last week, since the loads are non-reactive or purely resistive, then we know that the phase currents would be in phase with the phase voltage. All right. So this is what this is saying. The angle for IRY would be equal to 0. The angle for IYB would be at 240. And the angle for IBR would be 120 degrees. All right. So since the system is balanced, we basically can use one phase. All right. So the power PRY then would be equal to VRY, IRY cos the theta VRY, the phase angle for the voltage, and the phase angle for the current. You subtract those. And since they are in phase, same angles, cos 0 is equal to 1. So for each of the phases, the power factor will be 1, since they are purely resistive loads. So PRY is equal to VRY times IRY, and similarly, PYB is equal to VYB, IYB. All right, so referring to our diagram, we calculated IRY, but the diagram has it as I1. So I1 would be equal to PRY divided by VRY. So that gives me 25, and we know that would be just the magnitude. So as a phasor, it's 25 angle 0. Similarly, we work out I2. That comes out to be 15 and at angle 240. IBR works out to be 10 at angle 120. All right, so now that we have our currents, we have our phase currents, let's see what we need to find actually. Now, wattmeter has IR going through, wattmeter 1 has IR going through it. So it is reading IR, and it is connected between red and blue. So it is reading VRB, right? So this would be the positive polarity point, because notice that wattmeter 2 common negative terminal is also connected to B. So we know that this would be the positive point for wattmeter 1, and here would be the positive point. So wattmeter 1 is reading IR and it's reading VRB. And wattmeter 2 is reading IY. So IY going through wattmeter 2, and it is reading VYB. All right, so therefore, we haven't found yet. We need to find IR and IY and VRB. All right. All right. So, as usual, we check what's happening at each node. So IR would be equal to I1 minus I3. And that gives us, so we had calculated what I1 and I3 was before. So IR is equal to 31.225 at angle minus 16.1 degrees amps. And IY here would be equal to I2 minus I1. And that works out to be 35 at angle minus 158.21 amps. All right. Now, we know what VBR is. And we need to work out what VRB is. So one way you can do it graphically. VBR is at angle 120 degrees. So VRB would be 180 degrees from it, going in the other direction. So if you draw a straight line down, you know that you would end up somewhere at around minus 60, right? But you can do it this way. So VRB is equal to minus VBR. All right. So it's the 120 minus 180 because the minus sign is actually minus 1 and minus 1 in terms of angle now would be the 180 degrees. Right? 180 degrees away from 120 would be where VRB ends up. So it actually ends up now at 400 at angle minus 60 degrees. Or we could say 400 at 300 degrees. Right? All right. So now we do the calculation. So we have found out all the parameters that we need to find in terms of voltages and currents. So now we do the calculation. So V, the watt-meter power is given by VRB times IR times the cosine of the phasor difference between those two phasors. All right, so cosine of angle VRB minus the angle for IR. And put those into the formula. 400 times, so IR was 31.225. And cosine of minus 60. Minus 60 for the VRB. Minus 16.1 for the IR. So the watt-meter one reads almost 9,000 watts. Right? It would be 9,000 if we didn't have these kind of rounding off here. These rounded off. So 9,000 approximately. All right. And then we do the same kind of calculation for P for watt-meter 2. So it's reading VYB times IY times the cosine of the phasor difference between those two phasors. All right, so that works out to be 11,000 watts. All right, and then the theory says that the sum of the two watt-meter readings, so PT will be PW1 plus PW2, and that works out to be approximately 20 kilowatts. All right. Now, if you remember that the red yellow phase had 10 kilowatts, the yellow blue phase had 6 kilowatts, and the blue red phase had 4 kilowatts. So when you sum up those by the method that we know from before, you get 20 kilowatts. So the 2 watt-meter method that we used a while ago verifies that what we actually have in the circuit is calculated correctly. All right. So we have shown that the 2 watt-meter method can work for an unbalanced delta connected load. All right. So I'm going to give you a chance to work on this one now. So I will give you a few minutes. Before I say that, any questions so far? Any questions so far? All right. It's easier to write than to say it. Okay. All right. So everybody clear with what we have been doing so far? fairly straightforward, right?
Yes, sir.
No, sir, it's kind of fuzzy.
It's kind of fuzzy.
Yes.
You're talking about the picture?
No, we just did.
What we did? All right, tell me what was fuzzy. Can we go back?
Well, not really, sir, but we're kind of slow today, but yeah.
Yes, sir. You can always go back.
So just more for digest it still, you know. You see, kind of go too fast.
I was going too fast.
So much.
We never slow me down.
You can talk to your
For this.
Yes, you know, need to text me your start from March.
So you could just allow us to write out the question and then you can go back.
You want to write down the question?
Write out a picture of it, sir.
Okay, good. All right, so let's go back and see. All right. So the watt meter we're given a circuit, a delta connected circuit, and we were actually told what the loads were in each phase. Right. Now we're going to use that information to find phase currents, right? And the relevant line currents and line voltages. All right. Now, based on how the watt meters are connected, we can see that for watt meter 1, current IR is flowing through it, right? Which means that we will need to find IR. Also for watt meter 1, the voltage across it is RB, right? So we need to find VRB, right? So remember, R is considered to be at the higher polarity, right? And the common point would be at the lower polarity. So positive up here, negative down here. So we need VRB. Right? And for what? So that's for watt meter 1. We need IR and VRB. So these are things that we are keeping in our mind. So boy, these are things that we need to find. All right. Then if we look at watt meter 2, realize now that IY is flowing through watt meter 2's current coil. All right. Everybody clear?
Yes, sir.
Talk. Yeah. All right. And the voltage coil for watt meter 2 is connected between Y and B. All right. So we know that Y is at the positive potential, B is at the negative potential. Y is at the higher polarity, B at the lower polarity. All right. So we need VYB, but we know that already because we have defined that from before based on our phase sequence. So we have defined certain voltages already, VRY, VYB, and VBR. All right. Now, watt meter 1 said, boy, we need also VRB. So we need to bear that in mind. All right. Now, the next thing we needed to do was to find the phase currents. In order to find the line currents, and since this is an unbalanced system, we need to find the phase currents. We need to find all phase currents. All right? Everybody clear?
Yes, sir.
So why have to find all phase current again, sir?
Because we need line currents.
Okay.
Right. We won't be able to find the line currents without knowing what the phase currents are. Right? And since it's an unbalanced system, it's important now that you find the phase current in each phase. With me?
Yes, sir.
All right. Now, since it's, they tell us now that the loads are are non-reactive. So the question state them as non-reactive loads. Now, we know that non-reactive means that there's no inductance or capacitance in the load, which means then that it is purely resistive. A purely resistive load. Now, for a purely resistive load, so this is something that you need to know too, and always bear in mind. For a purely resistive load, the voltage phasor and the current phasors are in phase. Everybody clear? For a purely resistive load, the voltage phasor would be in phase with its corresponding current phasor. So for example, VRY is the voltage phasor for the red yellow phase. And IRY would be the current phasor for the same red yellow phase. Now for when the load in the red yellow phase is purely resistive, then VRY and IRY are going to be in phase. Everybody with me?
Yes, sir. It makes sense because the reactive portion would be 0.
Right. All right. And this follow on from something that we had done with the impedance triangle and those things from the first week. All right. But yes, so bear that in mind. And we can then write down the formula for power. We know what the formula is for power. It's VI cos theta. Remember? Power in per phase is V phase, I phase, cos theta for that phase. The phase difference between the voltage phase and the current phasor. All right. So we are being specific now when we state the phase. So it's VRY and IRY and cos theta VRY minus theta IRY. All right. Now we know that these for VRY and IRY are going to be at angle 0 because VRY was chosen as a reference, so it's at angle 0. So therefore IRY is going to be in phase with it, and it's going to be at angle 0 too. All right. Now cosine of 0 is equal to
1.
1, right? So that's why we end up with PRY is equal to VRY times IRY. So you could imagine that a times 1 is right here. It wouldn't change the thing, right? By the way, if you're writing the formula for power, if you're not writing I square R, make sure you write VI cos theta, right? Even if cos theta is 1, show me that you know that it's going to show me how you get it to be 1. Don't just assume that I know, because I usually forget everything at the most inappropriate times, like when marking papers. So we have a formula for the non-reactive load in the R yellow phase. Similar equations can be written for the YB phase and the BR phase because they are also purely resistive loads in those phases. Body clear?
Yes, sir.
Good. Conroy?
Yes, sir.
All right. All right, so we define our voltages, and we need now to work out, and we define what the formula for the power is. in each phase. So we need now to work out the current that is flowing in each phase. So the current in each phase, we are used to saying IRY, but notice that they have labeled it as I1. So I just use that also, right? Which is an important thing to do. Refer to, when you're referring to your circuit diagram, you should use the labels that you have there, right? So I1 has a magnitude of 25 amps. And because we know it's in phase with VRY, its angle is going to be 0 degrees. So it's 25 at angle 0 degrees. We can work out I2, which will be the current flowing in the yellow-blue phase. So it's the P yellow-blue divided by V yellow-blue. And that gives us the 15 amps. So I2 is 15 at angle 240 degrees. Clear?
Yes.
All right. And I3, similarly, we'll work it out same way. PBR divided by VBR. And that gives you 10 amps. And 10 amps at angle 120 degrees. All right. And by now you would know what each wattmeter is reading in terms of current and voltage. All right. So that's what is stated here. All right. So far we have we need now to take stock and see what we need to find. All right. So we need to find IR, we need to find IY, and we need to find VRB. We already have VYB, so we need to find VRB.
So, sir, so
Yes.
this means that if so, wattmeter 1 was the current coil was in the blue line, we would need to find IB.
Right. And in that case now, you would need to put the command line somewhere else, right?
Yes. All right, sir.
All right. So in the lab experiment that we do with the 2 wattmeter, we usually connect between red and yellow. Right. So yellow becomes the common one. And so 1 wattmeter current coil is in the red line, and the other wattmeter current coil is in the blue line, and yellow becomes the common. So you decide which one you want to choose, and any one of them you choose, you just know as anyone you choose as the common, you just know that the current coils will be going in the other 2 lines. All right.
Yes, sir.
All right. All right. I just remembered a joke. But I won't share it because it might bring somebody into disrepute. There's nobody in this class, though.
I can share it, sir.
No, there was somebody who knew of what was done in the lab, and so I figured out, but that's the only way it could be done. And so I had given a question kind of similar to this in a test. And he was there saying, no, this can't work. This can't work because that's not how we do it. I said, no, just follow the instructions and do it. And
I think we have an idea who, sir.
he probably spent about 3/4 of the exam just sitting down and said, no, this can't work. You know?
Oh boy. So we need so that means when they give us the question, we need to switch them around and try to work it.
Well, no, look, right, yeah, you can do that too, you know. Yes, you could do that, right? Anyone you choose as a common, you know that the other 2 now would have the current coils in them. All right, so anyone can be chosen. All right. All right, so we needed to find IR. So we'll go back to Kirchhoff's law now and look at what's happening at the nodes. So IR plus I3 would be equal to I1. So therefore IR is equal to I1 minus I3. All right, and that works out to be 31.225 at angle minus 16. Then we need also to find IY, which is flowing through wattmeter 2. So IY is equal to I2 minus I1, and that works out to be 35 at angle minus 158.21 degrees. All right, and remember we...
Sir,
Mr. Atkinson, you need to mute your mic.
ask me something, sir. Why wouldn't we need to find IB again?
Say that again.
Why wouldn't we need to find IB?
All right, what is IB doing? It not doing anything in terms of the watt meters. All right. Remember, so we only need to see what is happening.
Okay.
Okay. All right, so we need to find VRB, and VRB is actually minus VBR. And one we are working it out is to say, all right, what is angle for VBR? And take 180 degrees from it, because 180 degrees would make an about turn, right? Going in the opposite direction. So when I take 180 from 120, I get minus 60. All right. And if you can picture the Cartesian map or the Argon diagram, you will see that minus 60 would be opposite to 120, a straight line down. If you use a protractor measure, you will end up at minus 60, which is also equal to 300, right? 360 minus 60 would be 300 degrees. So I could have written it as 400 angle 300 degrees. All right, so now we have gathered all the data that we need to find in order now to be able to solve the problem. Find the power in each of the watt meters, read by each watt meter. So the power read by watt meter 1 is VRB times IR times the cosine of the phase angle between these two phases, between IR and VRB. All right, so that's what this equation is saying. All right, so VRB is minus 60 and IR is minus 16.1. So we put in the data, 400 times the 31.25 times the cosine of that, and we end up with almost 9,000 watts. 8999.683. All right. Also, so we find out what meter 1 is reading. We need now to find out what watt meter 2 is reading. So we go back to the equation that is governing its operation. So it's VYB times IY times the cosine of VYB, cosine of the angle for VYB minus the angle for IY. All right. All right, and then we work out, we substitute in the data that we know. VYB is at 240 and IY is at minus 158.21. Minus and minus will give you a plus here. So you find the cosine of that sum here. And then you work it. Yes.
So we didn't have to change to put a minus before this voltage because it already match up with the phase sequence.
Right. Right. It's with in the sequence, right? Yeah, this one is VYB. So, and we had defined what YB was already.
Yes.
We had 400 at angle 240.
Mm.
All right.
Yes, sir.
Right. So so with the sequence here, you work with the sequence that we have defined, and if we don't have any, we work to find those that are the one that we need to find. So one of them is going to be opposite to what we normally use. All right. The total power in this circuit then is the sum of each wattmeter readings, and that gives us the 20 kilowatts. And this is a verification of the phase value of the load in each phase, right? We know that this was 10, this was 6, and this was 4. If you add up all of them, you get the 20. So the wattmeter, the 2 wattmeter method verifies what we know as the phase value of the load. So we can say that the 2 wattmeter method was able to determine the total power in a 3-phase unbalanced delta circuit. All right. So the next question now, which is what I wanted you to do, is a balanced star connected system, 3-wire star system. So let's see if we can work out what the total power is in this 3-wire system, 3-wire star connected system. All right, so let me give you about 10 minutes then now to try it.
All right. Sir.
All right, so let's talk to it first though, so that everybody can get a good start. What's the first thing that you want to do? So yeah, the procedure that we normally employ when we're going to deal with any one of these problems.
Right, no matter how.
Good. Right on what you have, yes. All right.
So you find the phase currents.
Right. Right. So you need to find the phase currents. Good. Right. And then?
So you figure out what the wattmeter needs.
Good. Good. All right. Yeah. Pick a reference. All right. So what's the reference for our star system?
Red phase, sir.
Right.
Yeah.
Red phase current or red phase voltage or?
Red phase voltage, sir.
Right. Red phase voltage. All right. So good. All right. So it sounds like you're on the right path. So I'll give you 10 minutes.
Sir,
Yes.
the wattmeters are measuring active power, right?
Yes. Yes.
So is it that we just need to the load is both reactive and active.
Yeah.
So I kind of do we consider the reactive as well, or we just in terms of current, do we consider only the resistive part of it, since the wattmeter is measuring the active part of it?
No.
Okay, so we still use it to the whole load.
Right. Right.
All right.
Yeah, I guess the wattmeter is smart enough to distinguish between um, real and reactive.
Okay. All right.
to have Dunkin' go through.
Sir, all impedances are the same, right?
Yes, yes.
So we
Right, that's a each branch consists of a coil of resistance 4.2 ohm and 5.6 ohm reactance. All right, any progress?
Sir, I'm just able to find IR. I don't know if it's correct.
Okay. All right, let's see if it is.
So I get 32.86. But you have, but me not have the angle. Me have minus 23.13.
Minus 23.
0.13.
Hold on, I wonder if I put it in the wrong.
But I have 230.
No, sir, I got the same thing that you got.
It's 5.6, man. Yeah, 5.6. Right. Yeah, so the impedance should be 7 at angle 53.13.
I have one of it.
Sir.
That angle incorrect. All right.
Yes, it's a Bruce.
Sir, I just use the rectangular form, you know, sir. But the currents are different.
The currents are different.
In calculating, yeah.
I'm not sure what you mean.
Sir,
Difference
I know it's a balance system, but the magnitude of the currents I got are different.
Oh, but all right. So let's follow this then. Sorry. The phase voltage would be the line voltage divided by √3. Everybody with me?
Yes, sir.
All right. And then we're going to, as usual, VRN is our reference phasor for the star system. So VRN is 230.94 at angle 0. Therefore, VYN is 230.94 at angle 240. And VBN is 230.94 at angle 120. All right. Now, the same impedance is in each phase, right? So ZR is equal to ZY equal to ZB equal to 4.2 plus J 5.6. And that works out to be 7 at angle 53.13. All right, so if I want to find IR, it's VRN over ZR. So it's the 230.94 at angle 0 divided by 7 at angle 53.13. And that works out to be 32.991 at angle minus 53.13. All right.
So if we get
34 for the magnitude. That's not too much off.
Yeah, man, because you would have done some bad rounding off somewhere. What you use as your phase voltage?
230.940.
And what you got to the phase impedance?
I use the same 7 and 53.130. The only difference is that I use 3 decimal places.
But even so, you wouldn't get up to 34. So you got a 230.94 what?
Yeah.
No, man. So it wouldn't make any difference then.
Right, master. I'll try again.
Something wrong with the maths there. All right, so we work out IR, and we do a similar thing for IY.
IY is okay.
So it's VY divided by, I had ZR, but it's ZY and ZB. But you know, they are all the same anyway. I never said that before. But they're all the same. The same, all the impedances are the same. So if I'd write ZY here, to be more accurate, it should be ZY, and for IB, ZB. But they all have the same values anyway. Because we had stated before that ZR is equal to ZY equals ZB. So,
sir, for IY, you added 362 because I got
minus one.
The angle, the minus 173.13. You added 360 to that.
Yeah, you could do that. But what I did was just take 240 minus 53.13. Because when you're dividing, you subtract the angles. 240 minus 53.13. So that's how I end up with that.
All right, sir.
All right. And IB is at angle 66.87. All right. So what meter one reads IR and VRB, and what meter two reads IY and VYB. All right. So we need to find VRB and VYB. All right. So we hadn't found any line voltage before, but we now need to find them since the wattmeter is reading those. VYB for wattmeter 2 and VRB for wattmeter 1. So VRB would be equal to VRN minus VBN. Remember? So when we were defining our line voltages for the star system, you know, you take the first one minus the second one. So VRN minus VBN. So VRB works out to be 400 at angle minus 30. Everybody with me with that?
Yes, sir.
Sir.
Okay. So Paul? All right. So VRB is at 400 angle minus 30 volts. Right. And minus 30 is also 330. Right, from the positive side. Okay, Mr. Paul. All right, and VYB would be VYN minus VBN. So we just substitute in the values for VYN and VBN. So we get VYB is equal to 400 at angle 270. In your calculator, you might see minus 400I. Or if you use
Is that the same as minus 90, sir?
Right, right.
Okay. All right.
0 going, right. Yeah, minus I would be minus 90. Remember, I is angle 190 degrees, 1 at angle 90 degrees. So minus would be 1 at angle minus 90 degrees. Or 270 if you're measuring anti-clockwise. All right, so again, now we go back through now and we start to calculate the power read by each wattmeter. So wattmeter 1 is reading VRB times IR times the cosine of the phase difference between those two phases. So it's 400 times 32.991 times cos of VRB was at minus 30 and IR was at minus 53.13. So we get wattmeter 1 reading 12,135.62 watts. And the wattmeter 2 would be reading VYB times IY times the cosine of the angle, the phase difference between those two phases. All right. So VYB is at angle 270 and IY is at angle minus is angle 186.87. This is IY. All right. So the wattmeter 2 is reading 1,578.51 watts. Everybody okay with that?
Yes, sir. That's what I got, sir.
You got it. All right. Good, good.
Slightly off, sir. But yeah.
House light.
Just I got third for PW1, sir, I got 12,135.8. And then for PW2 I got 1,578.53.
Okay. All right. Well, we wouldn't split hairs about those. Yeah, that's all right.
All right, sir.
All right. So we add them up and we get the total power. And it works out to be 13,714.13 watts. All right. Or you could write it as kilowatts, 13.714 kilowatts. By the way, when you change from watts to kilowatts, do it way at the end. It's right at the end you should do it. Don't bother do it from way up here, so because you start to rounding off when you do that and lose some accuracy. All right, so let's verify what we have. We know what the phase power was, 3 VR we use for the red phase. It's 3 V phase, I phase, cos theta for that phase. So 3 VRN times IR cos theta VRN minus theta IR. All right, so 3 times the 230.94 times the 32.991. VRN was at angle 0 and IR was at minus 53. So the total power using what we know from before is 13,714.13 watts. All right.
Sir.
Yes.
Sir, the voltage we use in the formula to find power is a phase voltage, right, sir?
You mean for this second one here? We're not doing the verification?
No, sir, for wattmeter 1.
No, man, it's a line voltage. Look at it. It's between red and blue, you know. Remember the voltage between any two lines is a line voltage.
Oh, okay.
And the same thing with the wattmeter 2, BYB So using the 2 wattmeter method, you're actually using line current and line voltage. Line current. So for a star system, a line current is also phase current. Right? But line current and phase and line voltages are being used in the 2 wattmeter method. All right. Now, sorry. We can actually find the power factor of the system, by using the wattmeter readings. And these formulas tell you how to do it. The book has some proof, but I don't think you really need to know the proof. You only really need to know how to use the formula. All right, so it's a little bit kind of unwieldy, but let's say you find the total power. All right, so that is one thing that's called PT up there. You find the difference between the 2 wattmeters, and you use the larger readings as the PW1. So whatever your findings were before, you use the larger reading as PW1, and then you take away PW2 from that, multiply that numerator by √3, and you get a value. Then you take the tan inverse of that value, and you get an angle, and then you find cosine of that angle, and you get the power factor. All right. It's all more complicated than it is, so let us look at an example quickly. All right, so 2 wattmeters connected to measure the input to a balanced 3-phase circuit indicate 2,500 watts and 500 watts respectively. Find the power factor of the circuit when both readings are positive, and B, when the latter reading, so that will be the 500 watts, is obtained after reversing the connection to the current coil of one instrument. All right, so some of you may be familiar that sometimes when you're reading the wattmeter, you might see the needle deflect towards the left, like it's trying to go below 0. And if you flick the reverse switch, then you get a positive reading. So that's what part B is saying. When they when they flick the reverse switch, it got 500 in part B. So let us look at part A first, though. All right, so the total power according to wattmeter readings would be the 2,500 plus the 500, and that will give us the 3,000 watts. All right, then theta now would be equal to the tan inverse of √3 times PW1 minus PW2 over PT. So you could have made this a 2-step process like we did before. Find tan theta first, and then afterwards you find the theta. Yeah, maybe that's better. You do it that way, so you don't have any mix up.
But for you, is radians with that, sir?
No.
Okay.
No, man, straight. Degrees. So √3 times it 2,500 minus 500 divided by 300. It works out that the angle is 49.107. And then I find the cosine of that 49.107. And that works out to be 0.655. The thing with this, though, you can't tell whether or not it is a lagging or leading power factor. We're just using the readings. I guess we would have to know exactly what make up the load in the circuit to know whether or not it's lagging or leading. But the calculations alone won't tell you whether it's lagging or leading. All right. Now for part B, where the 500, you had to reverse one of the wattmeter current coil to get the 500. So, which means that in reality, PW2 is actually reading minus 500 watts, right? So the total power then would be this 2,500 minus the 500, give you 2,000. And then we go back through this again. But in this case now, the numerator is going to be larger than the denominator because you have a minus and a minus. Two minuses give you a plus. Right? So the angle works out to be 68.948 degrees, and the cosine of that angle works out to be 0.359. All right, so practice. Oh, you have a lot in the bird. You can get a lot of practice from these. So check the bird and read them and practice them. Finding the power factor from wattmeter readings. Where am I? Sorry. All right, power factor correction. Any questions on finding the power factor from the 2 wattmeter readings? Supposed to be fairly straightforward.
Yes, sir. The principle is straightforward.
Right. All right. Now, why do we need power factor correction? In industrial plants, you usually have a lot of motors and loads that are highly inductive. And because of that, now the power factor is usually low and is a lagging power factor, and it can become very poor. So anything below 0.8, would be considered fairly poor, and the lower it gets, then it's bad. So for example, the 0.36 here would be very poor. Even the 0.655 here would be poor. All right. Now, a poor power factor is also a costly thing and very inefficient. So, usually, plants try to make some effort to correct their power factor, and the public utility like JPS usually give people an incentive to correct their power factor, to have better power factor. The incentive basically is that you pay less for your bill, your light bill, and your power demand and all those things. So there's an incentive to have a better power factor. Plus, you want to improve your operational efficiency. All right. Now, the equipment that is used, one equipment that is used is a capacitor. All right. And I'm showing you some capacitors. So this will be a bank of 3 capacitors on a power line. Right. These cylindrical cans are transformers. So the capacitors are connected close to the transformers, usually connected close to the loads. Right? So when you're out on the street, you can look up and see, if you see these kind of rectangular shaped boxes, these would be the power capacitors. All right. For 3-phase system, it's usually referred to as a 3-phase bank, or a bank of 3. All right. Now, circuit diagrams to show you how the capacitors can be connected across. So they are connected in parallel with the load. So in both cases you have a delta connected load, and in this case here on the left you have delta connected capacitors, while on the right you have star connected capacitors. All right, so correcting the power factor means bringing the power factor closer to unity, closer to 1. Right. All right. And I think I was pointing out that the load can be either star or delta connected. It doesn't really matter. And the capacitors can be connected in a star or delta also. All right. Now this diagram, which consists of two right-angle triangles, essentially explain what is happening when you're doing power factor correction. All right, so this larger triangle that comprises S1, P, and Q1 is the system power triangle. The system power triangle before you do power factor correction. So the power factor angle was phi 1 for that original system. Now after you do your power factor correction by adding some capacitors or reactive power, capacitive reactance, you end up with this smaller triangle described by S2 P Q2. All right, and you notice now that this angle is smaller, and the cosine of a smaller angle is actually a larger fraction. All right, so the original system had this power factor P over S1, and then after the power factor correction, the new power factor will be given by P over S2, right? So QC here is indicating that some capacitive reactance was added, right? Reactive power due to the capacitor was added. All right. Now, if you remember how we draw the triangle, QC for the capacitor would be below 0, would be on the negative pole of the imaginary axis, right? So that's why this R of a Q is going down, right? Basically what we do, we add Q to Q1, QC to Q1 and end up with Q2. All right, so that's what this is saying. Q1 plus QC. So QC is a negative number, or you get a lower value. All right. Something else that you would need in your calculation is to know that tan of phi 2 is equal to Q2 over P, because sometimes you will need to know what. Yes.
Could you go over that last part? I didn't quite got what you said about the Q1 plus QC part. I don't understand how that one happened.
All right. So if you remember from the first week, for a capacitive reactive power, the triangle is actually upside down. So QC would be vertically down on the negative imaginary axis. So minus J, Q will be on the minus J axis. QC for the capacitance. And S2 and S for the capacitance would be below here, right? So P would be real, QC would be minus on a minus J axis, and S would be negative.
Right, so Q1 is real and QC is imaginary. Okay.
No, man. Q1 is also imaginary, but it's positive. This vertical line here is your imaginary axis.
Oh,
P is the real, Q is our imaginary. But you have positive imaginary like Q1, and you have negative imaginary like QC.
Sure, the positive aspect of it would behave like inductance, and the negative aspect would behave like would basically represent the capacitor, the reactive capacitance.
Right.
So, sir, is there a possibility that the triangle, you could add enough capacitors to the thing and bring it down, bring the diagram to a point where there's no inductive reactance?
Yes, right. There's no reactive power. Right. Yes, you could do that. There's also that in that case now S2 would be equal to P, right? Because remember S is equal to P plus JQ. Do I have that somewhere here? S is equal to P plus JQ. So if there are no Q's, then S and P would be equal. Right? Yes. So yes, it is possible, but then there's also a cost factor that you have to consider. And so one of the things that you have to consider now as the engineer would be, is it worthwhile to bring the power factor to unity? Can I afford it, or can I live with a 0.95 or some other value? So that's one of the questions that you would have to ask yourself. But theoretically, it's possible. All right.
Yes, sir.
Good. All right. So let's do a quick example. So 3 similar coils, each having a resistance of 4 ohm and an inductive reactance of 3.46 ohms, are connected in delta across a 400 volt 50 hertz 3-phase supply. All right. Everybody seems to like the 400 volts system. The Bird likes it. The Hughes likes it. I think maybe only the Wiley might give you some different values. All right. But anyway, it doesn't really matter. All right. So the question asks now to find the total real power drawn by the coils, the total reactive power drawn by them, and the apparent power drawn by them, the power factor of the coils, and then the reactive power supplied by a bank of 3 delta connected capacitors, which are designed to raise the system power factor to 0.85 lagging. All right. And then we must find the apparent power of the system after power factor correction. All right. So I could have just asked you to find this, because many times, many questions just go straight to this. Find the reactive power that would be required to raise the power factor to the 0.85 lagging. But I'm asking the question in such a way that you can see some other things also, right? Because you would still have to work out these even if you were not told that you need to work them out. All right, so let's get going. All right, so everybody understand the question. We have a load here, 3-phase load. Apparently the power factor is not what we would want it to be, and we want to raise the power factor up to 0.85 lagging. All right, so one of they ask us to do certain things, including finding the power factor of the existing system. All right, so as usual, let's get into what we know. So we know that Z is equal to R plus JXL. And so that was given 4 plus 3.46, J 3.46. So the impedance in each phase is 5.289 at angle 40.86. All right. right away I can tell what the power factor could be, or how to find the power factor. But we'll get into that a little more. Anybody know how you could find the power factor just from what we've talked about already?
That angle, sir, just cost the 40.86.
Right. Very good. All right. So this is a delta system, and VL is equal to V phase. All right. So we're using one phase since the system is balanced. And we're going to use VRY as our reference phasor. So VRY is 400 at angle 0. So IRY, we don't know which one is R and Y, I think, but we just, I should have put on some labels on these. All right. IRY is VRY over Z. So it's a 75.631. That's the current at angle minus 40.86. All right, so this is how you do it. 400 angle 0 divided by Z, 5.289 at angle 40.86. Gives me a current, a phase current of 75.631. All right, now the total power, since it's a balanced system, we just need to find the power in one phase and multiply by 3. So the total power then would be 3 V phase, I phase, cos the cosine of the phase angle between the current and the voltage phasors. So it's 3 times 400 times the 75.631 times the cos of 0 minus 40.86. All right, so the total power works out to be 68,640 watts, right? Or 68.641 kilowatts. So the first question was to find the total power. So we have done that. Then the next question was to find the total reactive power of the existing system. Right. So we have not looked at what the capacitor is doing yet, right? So reactive power is given by 3 VP IP sine theta. Right? So 3 VR IR sine theta VRY minus theta IRY. And that gives me 59,000 VARs. Right? 59.375 kilovars. All right. Then we're asked to find the apparent power of this system. So ST would be, one way of doing it is PT plus JQT. I could have found 3 V phase, I phase, and that would give me the answer too. All right. So S is equal to P is a 68.64 and J is a 59.375. So ST is 90.76 at angle 40.86 kVA. Right. And then power factor from the power triangle is equal to PT over ST. And it's a 0.75, it works out to be 0.7563. And since we know it's an inductive load, we know so it's lagging. Okay. We could also have found it this way using the value of the impedance. The impedances, resistance and impedance. And that gives me that also. Or we could find the cosine of the angle for the impedance, or the cosine of the angle for the apparent power. Both of them give me, all of them give me about the same thing. So several ways of working out the power factor. All right, so the power factor is 0.753 lagging, and they want to raise it up to 0.85 lagging. All right, might not look like they're going very far, but it's just the procedure we want to see how it's done. All right, so the power factor of the new system now, which will be cos theta 2, instead of phi 2 here, I'm using theta 2, since we have been using theta for power factor from before. So the cos theta 2 will be 0.85 lagging. That's the power factor of the new system after capacitors are added. So theta 2 now works out to be 31.79. So remember, theta 1 was 40.86. Theta 2 now is 31.79. All right, so we can use that value now to find out what Q2 is, the final value of Q for the new system. All right, so tan theta 2 is equal to Q2 opposite over adjacent, or rise over run. So tan theta, so Q2 then is equal to P times tan theta 2, and that works out to be 42,539.6 VARs. Right? Now QC is the difference between QT and Q2, right? So QC, which is what the capacitors have added to the system, is 59.37 minus 42.5 kVARs. So Q is equal to 16,834 VARs, or 16.835 kVARs. So that's what QC is equal to. Now, they want now to find the new apparent power of the system. So the new apparent power would be the PT plus the Q, the JQ2, and that works out to be the 68.64 plus J42.54 gives me 80,753.66 at angle 31.79. So the new apparent power is 80.754 kVARs. So adding the adding the capacitors has reduced my apparent power demand from 90.76 to 80.754, and it has improved my power factor from 0.75 to 0.85. All right.
So this question is well involved, sir.
Yeah. Yeah. All right. For your homework, I've given. There are some additional things I want you to do on this question. So the data is there before. Come on. Mouse not going back. All right, so the data is there from the problem. So what I've done now is to just ask some additional question, simple question. What is the line current before we did power factor correction? And what is the line current of the system now after power factor correction? And then this one, so those will be very simple. And this one, the capacitance per phase for the capacitor bank. So that one I gave you the answer. And here you can state any benefits of power factor correction that you have observed in this problem. All right, so that's something that you have to do tonight along with, let me hear what somebody is saying here. When is the first test? I don't remember, and I look on it on the schedule. I told myself today that I need to look back on the schedule. All right, so it's on the schedule. I just need to consult it. You can do so also. It's in the Google Classroom. All right. Come on. And then I have two questions here for your practice. All right. You can try start working them for tonight, and we can go through them in the tutorial tomorrow. Somebody's asking me what's the code for the Google Classroom. Send me an email if you haven't been invited yet. Tell me which class you're in and your ID number and email address and all and those things. And I will send you the link. I'll send you an invite. All right. Any questions? So one of these questions was taken from the Hughes and one was taken from the Bird. So if you go and practice in the 3 books, you should be all right also. All right. Any other questions?
Not at the moment, sir.
Yes, sir. What is the first test? Yeah, sir.
Yeah, I thought I just said that a while ago.
Oh, didn't hear you kind of tripped out.
Oh, you kind of chip out. Check the Google Classroom. It's in the schedule.
Oh, all right, sir.
I don't. I mean, answering like that because I don't remember. I need to go back and check myself. I know it was. I know it wasn't in week 3, so I wasn't too concerned about this week. But maybe next week you should look, right? You should check to see if it's next week. All right. All right. If there are no other questions, I think we can call it a night until tomorrow. So you have lots of things to do.
Sir, how will the test be administered? What?
Yes, sir.
I don't know yet. They were supposed to be setting up Moodle for me. That hasn't been done yet, so I don't know yet. But you would know in early enough time.
Some of us still can't access Moodle as well, sir.
I can't really either. I don't think my thing has been set up for Moodle either. So yeah, in previous times, basically what I've done is send you our tests, and you do it and send it back to me. So we would have like a class and send you the test, give you a time to do it, and you submit it as soon as possible after that. Scan so you'd have handwritten it, scan it back, and send it back to me. So that is the option that we might be considering, unless Moodle comes up for us. All right.
Okay, sir.
All right. Sorry, I can't be any clearer yet, but I kind of waiting to see what will happen with Moodle also.
All right, sir. Enjoy the rest of the evening.
All right. All right. Same to you and to everybody. Have a good night. So this is in the Google Classroom, whether it's the U1 associated with UTech or my personal one. As I said, anybody who doesn't have access to the Google Classroom is probably because you have not been invited. So just send me an email. I've invited all those who have had email addresses for. So you can send me and I will send you an invite from both classrooms. Any one of them you can get into. You just work with that. All right.
All right, sir.
All right. Take care, everybody.
Okay, sir.
All right, sir.
Okay, good.